Justin Miller, Pop Physics here. We continue onward, looking at some net electric fields. So, we're going to do a little problem here in a moment, but ultimately, we have noted that the net electric field at some location is the vector sum of the individual fields due to the individual point charges that are producing the electric field. Ultimately, that E hat field due to a collection of point charges is given by sigma E hat is equal to you have 1 at some location P plus E hat 2 at some location P plus plus E hat sub n at some location P. So we have to define a location in space which we are trying to determine what the net electric field is. That's some point P. And then we have these individual charges, Q1, Q2, and Q sub n, that produce their individual electric fields at those locations. So P is the point at which we are determining the net electric field. And E hat 1, E hat 2, and sigma E hat n are the fields, electric fields, due to the individual charges Q1, Q2, and Q sub n at the location P. So we should really put at P, at P, at P. So again, the point with this is we have to define a position in space in which we're trying to determine what the net electric field is before we can say what it is. So I put up a couple of charges and I say, what's the net electric field? And you say, where? Where do you want to know? Because there's all over in space and it's different magnitudes and different directions depending on which position in space you're at. So this is what we've got to go with. So let's do a problem, shall we? So here's the problem. Alright, so we're going to take 2 point charges, Q1 and Q2, give them some amount of charge, throw them into a coordinate system, and say, hey, they're at P1 and P2, what is the net electric field at some other location, P3? We'll do this twice, we'll do it for an easy case, and maybe one that's a little bit more elaborate, but nonetheless, here we go. So, we're going to take that Q1 is equal to 3 microcoulombs, let's say Q2 is equal to -5 microcoulombs, and this is going to be at P1, which has some coordinates. Let's say it is 0 and 0.5, and that'll be meters, and this Q2 will be at point P2, which we'll say is 0.5, 0 meters. Here we go. And let's say P3 is at the coordinates 0.5, 0.5 meters. So let's draw this out and say what we're trying to get at here. So let's do this. Got ourselves a nice little coordinate system here. Got ourselves the Y, got ourselves the X, and we're going to put 2 charges in here. We're going to put this charge at 0.5, so up here, let's say that's about 0.5. We're going to go ahead and put ourselves this plus, that's Q1 right there. And then at at 0.50, which should be about right there, we're going to go ahead and put us some Q2. Q1, Q2, great. Plus, minus, good. And then we're going to say, hey, we got this point P3 in space that we want to determine what the net electric field is. So that is 0.5, which would be right there. And let's just say that is the point P3. Let's not put it there, let's put it right. The question is, what is sigma E hat at P3? And we want this as a magnitude and a direction. So if we want the magnitude and direction, we first figure out what it is in unit vector notation and go from there. So what do we got with this? Well, we have two charges that each produce a field at that location. And it's the vector sum of those individual fields that we're interested in, the overall field at that location. So, let us do this. We've got to consider Q1. Well, Q1 is some radial distance away from this point, right? Some distance R1 away from it, and it's straight across from it, right? Because they're both at 0.5, this one's just over another 0.5. So what does the electric field look like due to this charge? Well, it's a certain magnitude depending on the distance away and this amount of charge, and it has a particular direction as well. What would that direction be? Radially outward from positive, right? So we have this. We have this E hat 1 at this point P3. Great. Well, we've also got this charge Q2. It is some radial distance away, you could say R2 from P3, and it produces an electric field just as well at the position P3. And what does that electric field look like? It's radially inward, because this is a negative charge. Radially inward with respect to somewhere directly above it would be straight on down. And there we go, we've got ourselves an E hat 2. We add those two vectors together, and we've got ourselves sigma E hat. So that's what we want to figure out. What direction and what magnitude is that total vector there? And then we can draw it out. So, we begin. Where do we want to start? We want to start by determining the magnitude and the directions of the individual vectors, individual electric field vectors due to the individual charges. So let's figure out, what is E hat 1 and what is E hat 2? Well, E hat 1 is going to be equal to K sub E times Q1 divided by R1 squared R hat. Great. So this resolves down into some things, right? So R hat with respect to Q1 is going to actually be in the I hat direction. So this is going to change to I hat. This is already positive, we're good. And this is then going to be equal to K sub E times Q1, which is 3 microcoulombs, 3 times 10 to the negative 6 coulombs, divided by its radial distance away, which is just going to be 0.5 meters, 0.5 meters, then quantity squared. And again, this R hat is now in the I hat direction. We could quantify that quite easily, could we not? Yeah, we just put it in a calculator. That's great. Let's just do it. Why not? We use 8.99 e to the 9th times 3 e to the negative 6 divided by 0.5 squared. And that looks okay. So I get 107,880. Then we go, well, what about the units? What are the units of the electric field? Electric field strength? Well, what do we have here? We have Newton meter squared per coulomb squared, and then we got 1 coulombs here, and then we got meters squared there. So then the unitization of the electric field strength has to be newtons per coulomb. And then we've got an I hat here. I hat. So there is the electric field's magnitude and direction at point P3 due to Q1. And then we've got Q2 as well. So we've got an E hat 2 is going to be equal to, well, that's K sub E times Q2 divided by R2 squared, R hat, which is going to be equal to K sub E times negative 5 times 10 to the negative 6. 5 times 10 to the negative 6 coulombs divided by the same 0.5 meters squared. And R hat with respect to Q2 would be, well, R hat is just the radial direction, so that would be in the positive J hat direction, the R hat. But there's this negative sign here, so really it's negative J hat, just as it's drawn there. So R hat itself is radial, and then plus or minus determines whether it's outward or inward. So I just put it in for plus here, minus there, tells us negative J hat, and we've got ourselves 8.99 e to the 9th times 5 e to the negative 6 divided by 0.5 squared. And we've got ourselves 179,800. Newtons per coulomb, and then it is negative J hat direction, negative J hat. So it's good to draw stuff out to make sure you're getting the right correlation with the direction, because it's sometimes easy to lose negative signs and such, but it's there. And there it is, negative J hat. So these are the two individual electric field vectors, do those two individual charges at that particular location. So then what do? We add them together. We have that the net field at P3 is equal to E hat 1 at P3 plus E hat 2 at P3. Well, if this only has an I hat component, this only has a J hat component. So we can actually write it out in unit vector notation and say that it is then equal to sigma E hat at P3 is then equal to 107,880 newtons per coulomb I hat minus 179,800 newtons per coulomb J hat. So there we've got ourselves the net electric field at P3 in unit vector notation. But we want it as the magnitude and direction, so we go ahead and figure out what is the magnitude and direction. So the magnitude, square root of the sum of the squares of the x and y components. This is again at P3 is going to be equal to the square root of this squared plus that squared. Square root of 107,880 newtons per coulomb quantity squared plus negative 179,800 newtons per coulomb quantity squared. Whew. And we get ourselves the magnitude. Being 209,681, call it 209,681 newtons per coulomb. All right, so we've got a pretty big magnitude. You say, well, those are really big numbers. That's okay. Pretty big charges, large amounts of charge, pretty close to them. We get strong electric fields locally. That's great. We also want the direction. So we've got theta sigma E hat at P3. The direction that it makes relative to the positive x direction is gotten by the arctangent of the sum of the y with the sum of the x. So we've got ourselves the arctangent of negative 179,880 divided by 107, oh, that's not 880, excuse me, 800, 107,880. Units per coulomb, sure. And then we've got in degrees. 179,800 divided by 107,880. Get negative 59.036. 59.036 degrees. So in the end, what do we get out of this? Well, we can write that sigma E hat at point P is equal to, we could start rounding stuff off to 3 significant figures if we wanted, or we could just keep it like this. I'm just gonna keep it, write this as 209,681 newtons per coulomb at an angle of negative 59.036 degrees. And then we can go make sure that that makes sense. Do we need to add 180 degrees onto this? Well, not according to this, because the x component is positive. It's just the y component that's negative. Let's look at this. This vector here is bigger than this one. This one has a magnitude of 179,800. And this one has a magnitude of 107,880. So maybe not scaled particularly well, but we didn't know before we drew it out, right? Let's draw direction. So this one we'll say is a bit longer. When we add these two together, this one should actually be quite a bit longer. This one's shorter. Like this. What do we get out of this? We'll erase that part. We've got a vector that looks like this. Sigma E hat at the point P. Does that look like negative 59 degrees? Yeah, there's theta right there. Theta matches up pretty good, pointing in the fourth quadrant, negative 59.036 degrees, sure. Got a magnitude, got a direction, it all makes sense. Fantastic. So there's one problem. Could we do another? Could. Yeah, let's hold on a second and erase this mess up. All right, so what do we want to do? Let's take the same two charges, Q1 and Q2 that we just dealt with. We'll put them at the same locations, P1 and P2. We'll just say, what's the electric field at a different location in space? A different P3, if you will. Or maybe we'll just call it P4. How about that? So again, we'll say that Q1 is 3 microcoulombs, and it is at 0.5 meters. Q2 is negative 5 microcoulombs at 0.5, 0 meters. And then we'll say P4 is where we want to now determine what the net electric field is. And we'll say P4 is at the location, let's do above, say 0.5, and then say 0.75. All right, so let's draw this out just to have some idea of what we're dealing with here. So again, let's take there, and there should be our charges. So we'll take this, is our Q1, this is our Q2, and this was our P3 right here. We want a P4 though, and P4 is just up a little bit more. So we go over 0.5 and then we go up 0.75. So there's 0.5, 0.75, about half that distance. So we're going to come up to right here now. So this is our P4. And the question is, what is sigma E hat at position P4? All right, so I'll get rid of that little P3 there. Say, let's do this, right? So, how do we approach it? The same way we did before. Just a little bit more work that we're going to have to do here because of this. Look at Q1 has some R1, which is not the same as it was before, and we have that the electric field that it produces is still radially outward, which is now that direction. So we can call that E hat 1 at P4. So there we go. Well, that's not just an I hat direction. That has both an I hat and J hat component. What about this one? Well, this point's still directly above this one. It's just higher up. We've got this distance, which we can call our R2 in this case. And we still have that it'd be radially inward down towards it. So we've got something like this. So we've got these two vectors that we want to add together, and this is our E hat 2 in this case. So we still have E hat 1 plus E hat 2 is going to be sigma E hat at the particular location. It's just a matter of figuring out, once again, what is E hat 1 and what is E hat 2. So let's just do this, right? E hat 1 at P4. Well, how are we going to get that? Well, we need to know what R1 is, and then we need to know what angle it makes relative to the positive x direction, so that at least we could write it as a magnitude and a direction, and then go from there. So let us start off with the magnitude. The magnitude of E hat 1 at P4 is going to be equal to K sub E multiplied by Q1 divided by R1 squared. That's just the magnitude, and typically we should take the absolute value, even though it's positive. It's just a good idea to make sure. We're just dealing with magnitudes, everything's positive here. So if we go ahead and compute this, we'll say, well, wait, we need to know what is R1 here. So when we want to get what R1 is, we can note that it's the hypotenuse of this triangle that's formed right here. We've got a base of 0.5, height of 0.25, and then we've got R1. So what's R1? Well, R1 squared is going to be that squared plus that squared. So R1 squared is going to be equal to 0.5 meters quantity squared plus 0.25 meters quantity squared. That's great. So at that, we can get what the magnitude of E hat 1 at P4 is K sub E multiplied by 3 times 10 to the negative 6 coulombs divided by that quantity there, which we'll just say is 0.5 meters squared plus 0.25 meters squared. We'll just leave it like that because that is R squared and that's what we want. So we'll go ahead and get that. We got 8.19. Let's do the negative 6 divided by the quantity of 0.5 squared plus 0.25 squared. And quantity. Okay. Got 86,304 newtons per coulomb. So there's the magnitude. Notice that's different than the magnitude we had before. It's less. Why? We're further away from that point. Excuse me, we're further away from the charge than we were at P3. So the magnitude's less. What about the direction? Well, the direction is gotten by noting this. That's what we're looking for. Theta with respect to the positive x direction. We can call this theta sub 1. Well, that theta there is equivalent to that theta there. How do we get that theta there? Arctangent, right? Theta is equal to the arctangent of opposite over adjacent, 0.25 divided by 0.5, which gives us, in degrees, tangent of 0.25, 26.565. 26.565 degrees. So there we go. We've got E hat 1. E hat 1 is equal to, and this is again at P4, is equal to 86,304 newtons per coulomb at 26.565 degrees relative to the positive x direction. That's great. We got it as a direction and magnitude, but what do we know? We're going to have to add this vector with another vector. And when we're adding vectors, we need things that mean a vector notation. So let's just go ahead, since we're already here, find its x and y components. We need E1x I hat and E1y j hat, so that we can add the vector with whatever E hat 2 may be. By inspection, E hat 2 is in the negative j hat direction, so that's going to be easy. But anyways, we want to get this. So we've got E1x hat, say, is going to be equal to the magnitude of E1 times the cosine of theta 1, which is this 86,304 times the cosine of 26.565. So just write it out. 86,304 newtons per coulomb times the cosine of 26.565 degrees gives us 6,034 times the cosine of 77,193. 77,193 newtons per coulomb, and that is I hat, X component. Likewise, we get the Y component, being the magnitude of E1, times the sine of a theta 1, which is 86,304 newtons per coulomb, times the sine, 26.565 degrees, and 8634 times the sine, 26.565. 38,596. 38,596 newtons per coulomb, and that is J hat. Positive I hat, positive J hat, yeah, that's it. It's pointing in the first quadrant. That's good, it seems reasonable. So in the end, we've got ourselves E hat 1 at P1 can be expressed as 77,193 newtons per coulomb I hat plus 38,596 newtons per coulomb J hat. That doesn't mean we're done. That just means that we found the electric field vector in unit vector notation due to Q1 at position P4. Now we've got to figure out, what about E2? Now get E hat 2 at P4. What's that going to be equal to? That's going to be equal to K sub E multiplied by Q2 divided by R2 squared. And this one, we'll just say R hat. Or we could just use the magnitude and say the direction has to be the negative J hat direction. Either way is good, but this is going to be negative R hat, and negative R hat is going to be radially inward, which is the negative J hat direction anyway. We need this first though, but that's easy to get because it's just above it, 0.7 meters, right? So we know that R2 is equal to 0.75 meters, and we go with this. So this is going to be equal to K sub E multiplied by -5 times 10 to the -6 coulombs divided by 0.75 meters, quantity squared. We've got R hat relative to Q, and point P would be J hat, and we've got a negative J hat there. And we quantify this out. We've got ourselves 8.99 e to the 9th. 6 divided by 0.75 squared gives us 79,911 newtons per coulomb, and it's in the negative J hat direction. Negative J hat. And that's it. It's already in unit vector notation now. So that's good. So now we can get what the vector sum is. We've got sigma E hat at P4 is equal to E hat 1 at P4 plus E hat 2 at P4, which is going to be equal to, well, we've got an I hat component, 77,193 newtons per coulomb I hat plus 38,596 newtons per coulomb J hat plus a negative 79911 newtons per coulomb J hat. So this stays the same, 77,193 newtons per coulomb I hat, and then this becomes 38596. Negative 41,315. Negative 41,315 newtons per coulomb J hat. So there is the vector sum in unit vector notation. What do we want? We want magnitude direction. So the magnitude, sigma E hat at P4 is going to be equal to the square root of the sum of the squares, which is just the square root of 77,193 newtons per coulomb squared plus negative 41,315 newtons per coulomb quantity squared. And what do we get? We've got that squared plus 77193 squared. So we get 87,554. 87,554 newtons per coulomb. So there's the overall magnitude, and then we need the direction as well. Theta sigma E hat at P4 is going to be gotten by the arctangent. The y component over the x component. Negative 41,315 divided by 77,193 is equal to tangent negative 41,315 divided by 77,193. Negative 28.156. 28.156 degrees. So sigma E hat at a P4 is 87,554 newtons per coulomb at an angle of negative 0.156 degrees relative to the positive x direction. What does that look like? We've got this vector, we've got this vector, and then we've got the vector sum of them ends up looking something like that, where there is theta sigma E, 28 degrees approximately below the positive x direction, and has a magnitude of 87,554. There you go, that looks different than it did at this location, right? Here was a lot steeper, 59 degrees was the net electric field, down like this. So, again, what's the net electric field due to these 2-point charges? What's the first question? Where do you want to know it? And then it's a matter of figuring it out from there. But you have to have a well-defined space in order to definitively say what it is as a magnitude and direction. Okay? These are grand problems. Good job. Stick with it. Electric fields everywhere. Watch out.